Mass and energy balance on open systems. First, let's go through the history and the development of mass balance in open systems. The ancient Greeks first proposed the idea that the total amount of matter in the universe is constant. Antoine Lavoisier described the law of conservation of mass as a fundamental principle of physics in 1789. Mikhail Lomonosov had previously expressed similar ideas in 1748 and proved them in experiments. Others who anticipated the work of Lavoisier include Joseph Black, Henry Cavendish, and Jean Ray. The law later is amended by Einstein in the law of conservation of mass energy. This law implies that the total mass and energy in a system remain constant. Thus, the theories were later developed and states that the number of atoms involved in a reaction remains unchanged in an open system. Now, let's talk about the history and development of energy balance in open systems. In 1824, Sadi Carnot defined work, and it is a critical key to the development of energy balance. Émile du Châtelet made a significant contribution to the growing theoretical framework of energy by suggesting a version of the law of conservation of energy that took kinetic energy into account. In 1842, the law of conservation of energy was discovered by Julius Robert Mayer. It is currently known as the first law of thermodynamics, which states that energy cannot be generated or destroyed in its simplest form. In 1843, James P. Joule independently found the mechanical equivalent in a series of experiments, demonstrating the existence of a quantifiable relationship between work and heat and therefore demonstrating that heat is a kind of energy. In 1876, Josiah Willard Gibbs established the notions of enthalpy and free energy, including the Gibbs free energy. These theories were eventually expanded and led to the open system energy balance equation. So, now let's look through at the definition and theory of mass balance for open systems. This is the simple 3D model for an open system. Mass balance, also called as a material balance, is a method of analyzing physical systems by using the principle of mass conservation. By applying the law of conservation of mass, all mass that enters a system must either leave it or accumulate inside it. Without chemical reactions, mass cannot be created and destroyed. Taking the cross-section that is shown, there is one inlet and outlet for the fluid to flow in and flow out. From the 3D model, we can know that the total amount of mass accumulated inside the system is equals to the difference between the total amount of mass that enters and leaves the system, where we can obtain equation 1. By differentiating equation 1 with time, the mass flow rate of the system is equals to the difference between mass flow rate of inlet and outlet. In steady state, the mass flow rate of the system equals to 0. Thus, the mass flow rate of the inlet will be equals to mass flow rate of outlet.
Now, let's take a look at the definition and theory for energy balance in an open system. Here's the sample of a 3D model for an open system. The energy input, output, consumption, or generation are all taken into account. All sources of thermal energy are placed on the input side of an energy balance, and all items of heat consumption are placed on the output side. We also need to know how much energy is being transported in and out of the system when calculating an energy balance. The law of conservation of energy states that energy cannot be generated or destroyed but can only be changed into other forms when the fluid within the control volume is evaluated. Based on the 3D model, when the open system is running, the system involves some important equations. First, work done is involved in an open system. There are two types of work, which are shaft work and flow work. Flow work is the energy necessary to push the entire fluid elements go through a distance into the control volume. Thus, the flow work equation is stated. Next, heat transfer to or from a system, also important in open system. Note that the signs for the rate of work is done on the system and rate of heat is transferred to the system is positive, while when rate of work is done from the system and rate of heat is transferred from the system is negative. Next, the total rate of energies for the specific portion of an open system is needed to be considered. It contains the rate of internal energy, rate of kinetic energy, and rate of potential energy. Therefore, total rate of energy accumulated inside the system is equal to the sum of total rate of energy entering the system, total rate of heat is added or removed, and the total rate of work done on the system or from the system. Then, minus the total rate of energy leave the system. Then, let's take a look at the derivation of the energy balance equation in an open system. Starting by substituting total rate of work equation into equation 1 to get equation 2. Next, substitute the rate of flow work and the total rate of energy equations into equation 2 to get equation 3. Then, the internal energy is replaced with the terms of specific enthalpy and PV into equation 3 to get equation 4 as stated. When the open system reaches steady state, substitute everything in the blue box into equation 4. Then, cancel all the PV terms and rearrange it to get final equation.
Next, let's us to look into an example. Pause the video and read the example. Now, let's solve the example by applying the knowledge of mass and energy balance for open system. First, we can illustrate a 3D model diagram for the turbine. Here is the information for inlet stream. Since the system is in steady state, the mass flow rate for the outlet stream is equal to the mass flow rate for the inlet stream, which is 300 kilograms per hour, and the velocity of the outlet stream 300 meters per second. Next, the different height between inlet and outlet is negative 5 meter. Shaft work at 1.5 kilojoule per second is delivered to the system. Calculate the rate of heat loss from the system when the specific enthalpy change is negative 650 kilojoule per kilogram. Now, let's us look into the solutions. We can solve the problem by using MATLAB software. For the mass balance, mass flow rate for outlet is equal to mass flow rate of inlet. Also, we need to change the unit from kilogram per hour to kilogram per second. Hence, the mass flow rate of the system is 0.0833 kilograms per second. By solving the energy balance, we apply the energy balance equation for the open system at steady state at the previous slide. We need to solve the rate change in kinetic energy, rate change in potential energy, and the rate change in enthalpy. By using MATLAB, the rate change in kinetic energy is 3.6 kilowatt. Next, the rate change in potential energy is negative 0.0041 kilowatt. To calculate the rate change in enthalpy, it is needed to multiply the mass flow rate, so the value is negative 54.1667 kilowatt. Then, substitute all the values into energy balance equation and the final answer for rate of heat loss is negative 52.0708 kilowatt. Before this video ends, here is the references for the mass and energy balance for open system. Thank you.